Alright, so welcome to your physics teacher. So I am Mr. Fernando, and today we're going to be looking at the conservation of energy and how we can connect it to the PHET simulation. So stay tuned. Alright, so a couple of things about this setup here. We're going to have grass along the ground, and we're going to assume that this U-ramp is going to be from a skateboarder U-ramp. I know skateboarding might be not so popular no more, but it's pretty cool. And at first you might think, oh wow, there's so many skateboarders in this U-ramp, looks pretty unsafe. But no. In this unit so far, I kept on telling you in previous videos that you should always be looking at this one object, but at multiple different positions with time. In other words, let's consider this to be the initial position, or time 0, t0. And now the skateboarder, possibly Tony Hawk, if you know who that is going down the ramp. So this is going to be T1, T2, T3, and T4. So it's just a single person, just at different frames in time. So today we want to show how energy is conserved, but to do that we need to make a couple of assumptions. First of all, the first assumption that we need to make about our system is we're going to assume this system to be an isolated system. So isolated system. All an isolated system is, it means that all the energy inside the system stays inside the system. So no energy can escape and no energy can come in. Likewise, our skater cannot suddenly escape. So matter also stays inside the system. So our isolated system is the first assumption we're going to make. And our second assumption is going to be about the U-track itself. The U-track is just where the skateboarder is going to be moving along. So we're going to assume that the U-track is frictionless. So we're not going to consider the force of friction in this case. So given these two assumptions, we can therefore say that all the energy changes that are going to be happening in our skateboarder is going to be due to potential energy changing and kinetic energy changing. Well, the sum of those two, kinetic and potential, is just called mechanical energy. So in this case, our mechanical energy is the total energy. Not always the case, but in this case, because we're defining kinetic energy as a half mv squared, which we studied the formula before, and potential energy as mgh. We're going to come up with another legend to study this situation. We're going to introduce bar charts. So we're going to use color coordinations here. Red will represent potential energy, blue kinetic energy, and black is our total energy, which in this case we're saying, because the only two energy we have is kinetic and potential, is the same thing as mechanical energy. That was a lot to take in, so try to breathe in. Now let's get back into work. Now work, that's a different formula. You might want to look at my previous lesson on work, right? So just click on the little icon that popped up. But let's look at potential energy. Potential energy, the formula is mgh. Now we study this formula, again, click on the link, there's another one. For potential energy, it depends on height. That means we need to define the coordinate system. In most questions, they always tell you to put the coordinate system at the ground level. But you're in this video, so I'm going to teach you the more clever way of thinking about it. You want to set it at the lowest possible point achieved by your object. The lowest possible point achieved by your object. So in this case, it's going to be at the very bottom of our ramp. So we're going to set up the coordinate system such that the height equals 0 at the lowest point that the object achieves. We do this because we need to set up the coordinate system for potential energy, because it depends on height. Now, as soon as we do this, we're setting up our zero potential line. Again, this might be confusing, but please, I keep on saying this, check out my other video where I talk about zero potential And that way you're going to get a better understanding of why I chose my coordinate system here. All right, so now we're going to look at the energy changes. We're going to assume that our object, skater, begins from rest. So if we're looking at a bar chart, there should be no kinetic energy. And given from our coordinate system, since it is at the highest point, it has the maximum amount of potential energy. So again, I'm using bar charts to represent this. And because our total energy, which is our mechanical energy in this case, is the sum of these two, they should give you the total energy, which in this case equals to all the potential energy. Great. Don't worry, it's going to make a bit more sense, so stay tuned, don't click out yet, stay with me. Now, as the skater is going down the ramp, the height is decreasing, right? So if the height is decreasing, what does that tell you about potential energy? The potential energy is also decreasing. So we expect that the bar chart for the potential energy to have decreased. But the energy just doesn't get destroyed or disappear. That energy is then converted into a different form of energy, into moving energy, right? Because the object is moving. Whoa, come on, you've been on a skateboard before. So it is moving, and therefore it has moving energy, which is a measurement of kinetic energy. So now it has gained kinetic energy. So our bar chart increased. And the sum of those two is our mechanical energy. That did not change because our system is isolated. Great. Don't worry, it's going to make a bit more sense. Stay with me. And once the skater reaches the lowest level, which we assume is zero potential, so our potential energy bar should be flat at its minimum. So all the energy is therefore converted into moving energy, so the maximum speed is at the bottom. Or another way to think about it, it has the maximum kinetic energy. So if it has the maximum kinetic energy, there's no potential energy there, in this case, but the mechanical energy remained unchanged. And I think now you're getting the point, right? Well, once the skater keeps on moving to the other side, now the height is increasing. So if the height increases, potential energy increases. But the only way for that to have increased is if the kinetic energy decreases. In other words, the object slows down. So our kinetic energy bar decreases, but the potential energy bar begins to increase. And the mechanical energy remains unchanged, so they should add up to the same amount from before. And once the object reaches the maximum height, which should be at the exact same height as before, we suspect that all the kinetic energy gets taken away by the force of gravity doing work on it. Another video that I made. So as it is moving up, the force of gravity is taking away energy from the object, which means it makes it slow down. So our kinetic energy goes to a minimum. And because the height is now at its maximum, all that energy has been converted into potential energy. And those two still add up to the mechanical energy, which has not changed throughout the whole motion. All right, let's put everything together now. So notice that throughout this whole motion, the mechanical energy did not change. So the bar chart representing that amount of energy remained unchanged. So the only thing that was changing is our potential energy. As the object is decreasing in height, it gets transferred over to kinetic energy, which makes the object speed up. At the bottom, where we set a coordinate system for zero potential, our potential is the lowest and our kinetic is the highest. And as it begins to move back up the ramp, the kinetic energy decreases, but the potential increases. And if it achieves the maximum height here, our kinetic is down to zero, our potential is fully maximized, which means this will be momentarily at rest. But throughout the whole motion, the mechanical energy remain unchanged. So one way to represent that is E mech for mechanical energy initial equals to mechanical energy final. We can move the mechanical energy initial to the other side. E mech final minus E mech initial. Well, here we have another difference that we saw before, right? There's a final minus initial. Whenever we have this scenario, you can just say, oh, that is the delta, or the change in mechanical energy equals to 0. So this is the law of conservation of energy. The energy changes equals to 0 for mechanical energy. So mechanical energy is conserved. So I'm going to show you a few more equations, but I'm going to put that in another video, the next video, and I'll show you how we can get the equations for the conservation of energy.